to speak here today, and I must say you guys have put together a really attractive program through this entire week, and I'm glad that I can participate. So I work in my research quite a bit with water, but a little bit at different scales of what I'm talking to you about today. So which is the water cycle, and we will look at the water cycle today from an ecosystem and global perspective. So what I would like to do today is I would like to say a few words about the water cycle in general. So what does that actually mean when we talk about the water cycle, and what are the most important components of the water cycle from the ecosystem perspective? And then I would like to give you three examples how humans interfere with the water cycle at various scales. And these interferences are land use, irrigation, and global change. So I would like to start with the figure that I also show in my lecture, which is the image from our planet from space. And when our astronauts first looked at our Earth from space in the 60s with the Apollo missions, they termed the blue marble, or the blue planet, suggesting that there is a lot of water on our planet, so that water is a very abundant commodity. But in order to understand the water cycle and also the problems that we have with water on our planet, it's important to look at this image in a little bit more detail. And I'm showing you here the same image with the water being removed from the planet. And what this shows us that actually the surface that water covers is very, very large, but it doesn't go very deep. So this water film across the planet is actually a very thin film that covers our planet, and this gives us this blue appearance, and potentially the wrong impression that there isn't that much water on our planet to begin with. And that actually becomes even clearer if we look at the different water pools that we have on our planet. So this bubble here is all the water that we find on our planet. And if we zoom into this a little bit in more detail and look at the amount of fresh water that's available on or that exists on our planet, so water that we don't find in oceans and water that is relevant for plants and also as humans, we see it's actually very, very little. And if we then consider that the majority of this fresh water is in fact captured in glaciers, in particular here at the polar caps, so in Greenland and in Antarctica, the fresh water that is actually moving around our planet and that is sustaining life on our planet is actually a tiny, tiny, tiny amount. So this shows us, although our planet is blue from space and it seems to be a lot of water on our planet, water is actually very, very scarce. Nevertheless, and fresh water is in particular scarce. This little tiny amount of water, so this little tiny droplet here, shapes the appearance of our terrestrial surfaces and our terrestrial ecosystems quite dramatically. So in this upper panel, you can show how this tiny amount of fresh water is introduced into terrestrial ecosystems by precipitation. So it essentially shows you the amount of rainfall and how it's distributed across the planet. And if you compare that to the biomass production across our planet, you will easily find that there is a very tight correlation between the amount of precipitation and the amount of biomass produced in terrestrial ecosystems. Now, as a consequence of that, water is responsible for many of what we call ecosystem goods and services that we as society depend on. And I just want to list a few here. First of all, water, of course, that's in the oceans, but also in fresh water, is home to animals that we extract from these aquatic systems and use as food, like these fish here. But then water, most importantly, when we talk about terrestrial systems, supports plant life. And I will talk about that quite a bit in the remaining talk today. And plant life delivers food for us humans, either directly in forms of fruit or grains or vegetables, but also indirectly by being food to animals that we then eventually eat. So we ultimately depend on water sustaining plant life for our daily dietary needs as human. And there is no technology that allows us to really avoid that. And then there are other ecosystem services related or products that are related to the productivity of plants that we utilize quite a bit. You can see timber here, and timber is still a very important commodity that we extract from ecosystems for construction, for pulp in particular, paper, tissues, and so on, but also for furniture. So there are many ecosystem goods that depend on the availability of water that we as humans and that our human societies depend on. But there is more to that. Water is also an ecosystem service that we utilize. So in the shape of the ecosystem and the processes in the ecosystem determine much of the quality of water that comes out of systems. Water determines the energy fluxes in terrestrial ecosystems. You can see an aerial infrared image of a section of the city of Basel here. And you can see there are roads here and rooftops that are red and green, so relatively hot compared to vegetation here that consumes water and that locally cools the environment. But ecosystems do not only provide water as a service, ecosystems also can retain or control the flow of water, and by doing that, control water as a service or potentially as a threat. So there are, as you can see easily here, is that there are many processes in ecosystems that are tightly related to water that matter for us humans. Now I'm a plant biologist, and I'm of course primarily interested in the role of plants in terrestrial ecosystems. And I showed you before, plant growth is heavily dependent on water. And before I would like to discuss this very simple cartoon here of an ecosystem water balance, I'd quickly say a few words why plants actually need so much water. Well, first of all, plants, as all life, originates from aquatic habitats, and particularly from the ocean. So the inside of plants, the inside of cells, contains pretty much entirely, or consists pretty much entirely of water. So all life-sustaining functions in the plant occur in water. So in the inside, a plant is really wet, if you want so. And what you can see here is a cross-section of the leaf, And you all know that one process that distinguishes plants from all other organisms is their ability to take up CO2 from the atmosphere and to perform photosynthesis. Now, a key requirement for the photosynthesis is that CO2 can actually enter the leaf. And leaves are typically sealed with waxy layers from the environment. You can see this waxy cuticle layer on top of the leaf, and there's also such a waxy layer on top of the leaf that is impermeable to CO2, and it's particularly impermeable for water. So it makes sure that leaves don't dry out very rapidly. But still, there are these tiny pores here at the bottom of leaves that allow CO2 to diffuse into the leaf. And this is absolutely necessary, because without this diffusional uptake of CO2, plants couldn't perform photosynthesis. Now, the problem is that as soon as these little pores are opened, massive amounts of water escape out of the leaf into the atmosphere. This is a process that we call transpiration. And it is the reason why you have to water your plants in your living room so that they don't fall dry, dehydrate, and eventually die. And the amount of water that is lost per unit of CO2 given up is huge. So on average, and depending, of course, a bit on different species and so on, but this can be up to 1,000 molecules of water that are being lost for a molecule of water that's taken up for photosynthesis. So at a global scale, this loss of water through the leaves of plants, we call this transpiration. Plant transpiration is a major water flux. So if we look at the water cycle in a terrestrial ecosystem, there are essentially three processes that we need to take into account. One process is where does the water actually come from in an ecosystem, and that is largely precipitation. And then a majority of that precipitation that enters terrestrial ecosystems is actually returned back to the atmosphere through plant transpiration. There's a little bit of evapotranspiration here from abiotic surfaces, but about 80% of the water that is entering the system through precipitation is returned at a global scale through plant transpiration. And the remaining water, everything that is not returned, actually leaves the system through runoff. And this can be at the surface, it can be in rivers, but it can also be down and below the ground as groundwater. So runoff, of course, is an important commodity that is important for many societies because we use this water. And the extent of runoff is largely influenced by the amount of water consumed by plants here through evapotranspiration. So the water balance of an ecosystem is actually very, very simple. You need to know what comes in. You roughly need to account for what's being consumed by plants, and the rest ends up as runoff. And I would like to now show you two examples how humans change, without probably always knowing that, the water balance of terrestrial ecosystems by changing the land use or changing the composition of the vegetation. The first example comes from Australia, from the southeast of Australia, from Victoria, where there have been large incentives to plant pine trees and eucalypt trees, which are rapidly growing trees, for timber production, but also for sequestering atmospheric CO2 in biomass. Now the problem is, even in Victoria, which is not the hottest part of Australia, but still, cities depend in their water supply quite heavily on runoff coming from the surrounding ecosystems. Now, this is something that wasn't really taken into account when these plantations were established. But the consequence of these plantations, in particular of these eucalypt plantations, which are very, very water demanding trees, was that the ecosystem water balance changed from a system with a low evapotranspiration where these temperate grasslands, to systems with very high transpiration once they were converted to these eucalypt or pine plantations. And you can see this very nicely here in this figure, that is with increasing stand age of these plantations, so with increasing tree size, the runoff changed quite dramatically, so by up to 400 millimeters. And if you think that here in Basel we have about 800 to 900 millimeters of precipitation per year, this is quite dramatic. And if you want to manage your ecosystems to supply drinking water to urban areas, then you're a dilemma. On the one side, you want to plant trees to sequester carbon. On the other side, this costs you a lot of water. So this very nice term, trading carbon for water when you're planting trees in arid regions. You can also tell the flip side of the story with deforesting. So this is an example from the Pacific Northwest of North America. Natural vegetation there are large and extensive coniferous forests, very valuable timber. And these are typically high rainfall areas, so a completely different situation as in Victoria, in Australia, as I've shown you a few minutes ago. Now here, the ecosystems were changed through land use from high evapotranspiration systems, evapotranspiration driven by these extensive coniferous forests, to essentially bare land with hardly any vegetation. And this is what happened to the runoff. So the area deforested in a watershed is linearly related to the runoff coming out of the system. With the equation that I've just shown you before, this is pure logic, right? That's not very hard to understand. The consequence, of course, is that the river systems were not adapted to this, because they were adapted to watersheds with much lower runoff. So in situations of heavy rain events now, these river systems couldn't carry the runoff anymore, and this generated flooding. So depending on how you look at this, afforestation or deforestation can be on the good or on the bad side. I mean, it's a completely human perspective. It can cause dryness or it can cause flooding. But the point is that land use activities, changing the vegetational composition of a terrestrial ecosystem, has direct impacts on the way the water that is available or becoming available through precipitation is split into evapotranspiration and runoff. Now, the second example how we interfere with the water cycle is not through indirect measures by manipulating the vegetation that is actually consuming water, but is by supplying additional water to the vegetation. So we actually have to expand our water balance equation for one more term here, which is irrigation. And you don't need to know, or actually withdrawal if you take water out of the runoff. So we're actually adding water to the system, or if we take water out of the system for irrigation. Now, why do we do that? Well, as I've shown you before, plants to perform photosynthesis consume quite a lot of water. And if we convert that into what we call the water use efficiency of crops, so if we ask ourselves how much water do we actually need to produce 1 kilogram of crop, you will see that depending on what crop variety you look at, it needs about 320 to 500 kilograms or liters of water to produce 1 kilogram of grain or 1 kilogram of potatoes or whatever you want to look at. So crops vary a little bit, but at the bottom line here, we need a lot of water to produce our food. And in many areas, like in Switzerland, this water is supplied by precipitation. But there are many areas on the world where there is not sufficient precipitation to allow rain-fed agriculture. So where this water has to be supplied, and there are typically two sources. This can come from rivers. So you dam rivers and you pump the water out of the river and you irrigate it into the fields, or you drill into the groundwater and partly even in fossil groundwater sources and pump the water to the surface. If you look at the global consumption of water and you look at, okay, who is actually using all our water resources, you'll see easily that the largest water consumer is in fact agriculture. It's much more than industry. It's much more than the power industry through building the dams. And it's much more also than our municipal water use in private households, for example. So agriculture, by producing our food, I don't want to point a finger to agriculture. I'm very happy that they are producing, or that agriculture is producing my food, but we need to be aware that this comes at a price. And one price is that agriculture is a very water expensive business. If you look at the global extent of irrigation, where does it occur and to which fraction of land area, you can see that irrigation, even in our temperate systems here, is a very, very widely distributed approach in agriculture. So it's not something that you only find in desert systems. It's really a very common agricultural practice in explaining the massive amounts of water that are being extracted from our natural aquifers. Some of you that, when you are still able to travel, might have seen images like that from a plane. So these are actually irrigated crop fields. So you can see these circles here. These are irrigation pipes that circle across the field. So they are probably a couple hundred meters in diameter. And you can see everything inside the circle is green and everything outside these circles is barren because there is not enough water for crop production. And if you look at the total numbers, about 25%, so a quarter of all freshwater runoff, so mainly this is in rivers, is today withdrawn for human use. And most of that goes into systems like that. And the scary thing is when we talk about sustainability is that 5 to 25% of the freshwater use exceeds the long-term supply. So we're actually depleting a resource beyond its ability to regenerate. And in fact, some of the world's largest rivers, the Nile or the Yellow River in China or the Colorado River in the United States, they have been, and those are huge watersheds that they drain, have been transferred into highly stabilized, and in some cases, like the Colorado River, non-discharging systems. So in dry summers, they don't even reach the ocean anymore. And the impacts, I don't want to talk about the environmental impacts of irrigation too much, but of course are quite wide-ranging. They reach from the salinization of soils and certainly also into the destruction of these the aquatic systems where the water is withdrawn from. So we are changing the water balance or the water cycle of ecosystems by manipulating the vegetation. That has a dramatic effect how water flows and cycles within the system. But we're also changing the ecosystem water balances by addition or adding or irrigating water or withdrawing water from certain systems. That's the second most important aspect, how humans interfere with the water cycle. And then there is a third aspect, which is an indirect impact on the water cycle again, which comes through a changing climate. Now, when we talk about climate change, we're all aware that CO2 is rising in the atmosphere, and we're all aware, at least the science part of our society, that this causes rising temperatures in the atmosphere, and there is a lot of scientific evidence that these two processes that I'm showing you here are mechanistically very tightly connected. Now, as I mentioned in the beginning, I'm a plant scientist and I work a lot on plant-water relations. So we are, of course, very interested to understand, so what does climate change mean for the water relations of plants? And in the last couple of years in Switzerland, we have experienced quite a few hot and dry summers, and drought, of course, is a huge topic. And in the meantime, everybody seems to agree that with climate change, this also means that we are having more droughts and in general, dry conditions. However, if you look into the data a little bit more carefully, the situation is not that easy. So we don't understand really yet how climate change is impacting one important component of the water cycle, which is the input of water into ecosystems, which is precipitation, which is the source, the primary source of water for plants. So you can see here data for Switzerland from one of the, this is actually a little bit of an older report, but the newer reports look, because it's still exactly the same. And you can see instrumental data here all the way until the early 2000s. And then these are here simulated data. And what we can see is that for winter, precipitation has in fact increased in Switzerland until about the 60s and has been quite stable since, so at least there are no trends over time relative to the long-term mean. And in summer, it's been very, very stable. So we cannot say today that there is a visible trend of less precipitation in the summer months in Switzerland. And if at all, if you look at the global, if the annual means, and so if you build the sum of winter and summer, precipitation actually has slightly increased. And then there are a few model predictions that suggest, well, in the winter, the precipitation is going to stay more or less the same. And then there are a few model predictions, but with quite a lot of uncertainty, suggesting that, well, in 2070, there might actually be a little bit less of summer precipitation because the Mediterranean climate is shifting slightly northwards, but the uncertainties are large. But why are we then talking about drought, if this is not evident from the data? Well, in order to understand that, in particular from a plant side, we quickly need to go back into plant physiology and need to understand why is it that plants are losing so much water when they take up CO2, and what's driving that? So again, you can see this leaf image here that you're already familiar with, cross-section of the leaf. You have here the vessel that delivers water into the leaf, and you have the stomates here through which water molecules can escape into the atmosphere. Now, how much water is going out of these pores and ultimately depends how much water is being sucked out of the ecosystem by the entire plant and released into the atmosphere depends essentially on three factors. It depends on the stomatal conductance, so how widely actually are these pores open? So how open are these gateways for water to escape? It depends on the total leaf area. Very easy to understand. The more leaves there are, of course, the more evaporative surface there is, so the more water can be transpired to the atmosphere. And third of all, and this is now where it becomes important, it also depends on the VPD, which is the vapor pressure deficit. And the vapor pressure deficit essentially is the force that pulls the water out of the leaf. And in a bit more trivial terms, the vapor pressure deficit is the humidity of the atmosphere. In a humid atmosphere, when the vapor pressure deficit would be low, plants would use relatively little water. If the atmosphere is very dry, plants would use large amounts of water. I always in my lectures make that analogy to drying your clothes. If you put a wet t-shirt that you want to dry into a wet atmosphere, like in a damp bathroom, it's not going to dry very quickly because you have a low VPD or a high relative humidity surrounding that t-shirt. If you put that wet t-shirt into dry air on your balcony in the full sun, it's going to dry very, very quickly because it's in a dry atmosphere. So there is a high VPD that pulls that water out of your t-shirt. And a leaf with its stomates open is very similar to a wet t-shirt. So with a high VPD, it's losing lots of water. So how is that connected to climate change? Well, when we talk about climate change, we often talk about temperature. And we very often talk about precipitation with not so clear data. But one thing that is very clear is that our atmosphere is becoming drier. And the reason for that is that our air on the continents is warming faster than the water of the oceans. So the oceans are actually evaporating less water. So what you can see here is not relative humidity, but it's the inverse of relative humidity, the vapor pressure deficit. And you can see that the vapor pressure deficit has been increasing quite dramatically in the past decades, and it's projected to further increase as a direct consequence of a faster warming of the continents than the ocean. So climate change leads to a drying atmosphere. And from an ecosystem water balance perspective, this means that we have higher evapotranspiration rates. So there is more water that's being sucked out of the trees. And as a consequence, the ecosystems are drying out faster. So the soil reservoir that is available for plants is depleted much faster in a warmer, drier atmosphere climate compared to the old climates, I'd say, so a couple of decades ago. And if we look at that now from a Basel perspective, so these are data from the climate station Basel-Binningen, and if we plot for the last 120 years here relative to the 1980 to 2010 reference, the anomalies in precipitation and vapor pressure deficit, and we look just at the last couple of years and a few extreme years in the historic record, like 1911 and 1947, we can see that there is a massive accumulation of dry years here in the last couple of years. And if you look at why are these years particularly dry, you will see it's not necessarily because of precipitation, because there have been similarly low precipitation years here as for 2015 or as for 2020. So there have been actually quite many years in the past that have seen less precipitation. But if you look at it from the VPD perspective, you can see that all these years here have experienced very, very dry atmospheres. And these dry atmospheres are partly causing these ecosystem droughts with impacts on forests that we have experienced in the past couple of years, in particular in 2018. You can see this image here is from the Hartwald in Basel. So we're manipulating the global water balance through changing the vegetation. We are playing around as humans with the global water balance by water withdrawal and large-scale irrigation. And we are manipulating the water balance of global ecosystems by changing the evaporative conditions through climate change, which is not only creating a warmer, but also a drier atmosphere and accelerates evaporative water loss and the drainage of water and the drying of ecosystems, which then can lead to drought events, as you can see here. With that, I'm at the end. And I think, yes, we have a blue planet. And the planet is blue, not because there is a lot of water, but because the little bit of water that is on our planet does really matter for terrestrial ecosystems that we, as humans, in the end, depend on. And we should know what we do with it, because it's important. And with that, I'm at the end and happy to take some questions.